I recently made a video where I was exploring the difference in output between merged and unmerged LoRa models. And through that analysis and through kind of trying out different experiments, I came to a conclusion that the difference between the forward pass of a unmerged model, where you have the LoRa adapters kind of acting independently, versus a merged model, where you have a single base layer weight into which the LoRa adapters have been merged, is the result of the difference in outputs. When you look at the, literally the, merged outputs minus the unmerged outputs and look at the absolute mean value difference. But I didn't feel like I had a great intuition, and I wanted to dig into it a little bit more. So I'm making this video where I'm going to run some very, very small experiments to start building some intuition around this. And yeah, I think I'll just leave that for the intro and that's it. So the one caveat that I had to remind myself as I was looking through this is that this analysis that I'm going to show does not apply generally to neural networks or LoRa adapters or transformers. This is a toy example. And no matter how much I am compelled to extrapolate the results to actual models and other in real applications or training or inference or whatever, I just don't think I can do that. So that being said, I don't think there aren't lessons to be learned, but this is more of a let's just kind of look at some simple things to get a sense of how things happen. So I have a few sections, and in the first few sections, I'm going to look at the output of linear layers versus the output or the product of matrix multiplication for a single layer, for two layers, and for three layers. Then I'm going to look at the linear output versus the LoRa merge comparison, or kind of analogous to LoRa merged operations, where you have the base layer weight and then you add LoRa B matrix product with LoRa A to get your merged weights. So I'm going to do that, which involves three layers, three linear layers. Then I'm going to look at sequential linear output versus merged linear output. And so in both of these cases, I'm using linear layers, but in one, they're separate linear layers in a sequence. And then in one, I'm merging the weights into the linear layer and then doing a forward pass. I'm going to do that for those three layers. Then I'm going to do that for mixed precision. I'm going to summarize those results, and then I'm going to do, I guess, an ablation where I'm going to look at different matrix sizes for these different types of precisions, and then look at the error between the linear output and the merged output, or sequential and merged output. So that's an overview of what this looks like. So starting off with the single layer, I have a linear layer without bias because I'm imitating what is done for the LoRa layers. And I'm picking a small size, so it's 32 by 32 with a 1 by 32 input. These are both float 32. Here is the forward pass through the linear layer, and here are my 32 outputs. And then here is the matrix multiplication using the weight of the linear layer, so x matrix product weight transposed. And there's no bias, so I don't have to add bias. And just visually inspecting this, this looks the same, or at least similar, up to 4 decimal places. If I use the default tolerance for torch all close, these are close. And then if I look at the actual percent difference, so I'm taking the average of the linear output, the average of the merged or the matmul output, I'm taking the absolute mean difference, and then to make it a relative difference, I'm dividing it by the mean value of the linear output, and then taking the absolute value of that, and that's this percentage here, which is 0. So this is like a nice baseline. My linear layer forward pass is equal to the linear layer matrix linear layer weight matrix multiplication. So yeah, good baseline. All right, so now we expand it to 2 layers. So now, again, I'm kind of imitating LoRa, where one of the layers kind of down projects to the rank of LoRa, and then the other one up projects. These are again float 32. Here is the output of the linear forward pass. So I'm taking X, forward pass through A, forward pass of that output through B, and I get this. And then I'm taking the matrix product and then transposing that. So this is kind of like my merged weight and then matrix product with the input. And again, we look upon inspection, looks pretty similar. And torch all close agrees. But now we can start to see, like, now we're seeing some differences, right? So the diff and the relative diff are non-zero. I mean, for all intents and purposes, they're zero, right? 1/1,000,000th as a percentage. So what would that be? Like 1/10,000th of a percent. So obviously that's pretty negligible, but it's not zero, and I think that it's important to point out. Okay, and then the last thing I do with this setup is I add one more matrix, linear layer, which is C. These are all now size 32. I have my linear output. I have my merged output. Upon visual inspection, they look pretty much the same. Torch all close says they're close enough. And we look at the percentage difference, and they're effectively the same, but still not zero. Okay, so what can I tell from that? What can I conclude from that? Again, I don't want to conclude too much, but I can say that multiple layers forward pass is different than a multiple layers matrix multiplication, whereas a single layer, it is going to be zero. Okay, so that was kind of the first set of experiments. Now we're going to not only have multiple layers, but we're going to have multiple operations. So what I'm doing here is I'm mimicking the forward pass, generally speaking, of the LoRa adapters, where I first get the output of the base layer. So, let's imagine that linear layer O is, quote unquote, our base layer. And then I do the output through the LoRa layers and add that to the output of the base layer. So that gives me an output there. And then I'm going to do the same thing, or kind of equivalent operation, but I'm going to do it with matrix multiplication. So this is like our base layer output plus our LoRa layer output. And visually inspecting these, again, they look pretty similar. They're close enough. And again, they have a non-zero relative difference when we look at the average values. Okay, cool. So that's linear output with 2 operations. Then we have, let's see, this one is pretty much the same. Well, the first half is the same. I have my 3 matrices. I'm going to do my kind of LoRa mimicking forward pass. But then now what I'm going to do is I'm going to make a new linear layer, and I'm going to replace its weight with the quote-unquote merged weight. So this is how I would merge the LoRa weights, more or less. I don't have the scaling factor. I think that's pretty much it that's missing. So not matrix multiplication, but now it's kind of, sequential linear versus a merged linear. And again, visual inspection of these two looks the same. It's close enough. And if we look at the percentage, it's still, really small, 10,000th of a percent. And let's see, yeah. So this next step is kind of expanding the same operation. So I have the 3 linear layers, I have the forward pass, and then I'm merging them into a new linear layer and doing a forward pass. Except now I want to iterate over different floating types. So everything up until this point, we've been looking at float 32s. But now I want to look at from float 64 up to bfloat 16. So I just basically just throwing everything into a function, and printing things out as we go. And so we're going to look at each one of these. So float 64, percent difference is 2 to the negative 15. Float 32, it's now 1 to the negative 6. Float 16 is now 0.003. So at this point, it's like, okay, 0.3%. This is now not zero and not negligible. And B float 16, okay, now we're at 2%. So that's certainly not negligible. So that was interesting to see. So I think what this tells me, reflecting back on the merged LoRa versus the unmerged LoRa, is that yes, the difference in merged and sequential forward passes is there. It's not negligible, or maybe it's negligible, but it's not zero. But there's also this added factor of precision. So precision also plays a part in how these differences propagate throughout the two different equivalent operations, but concretely different matrices that we're dealing with. So now we're getting somewhere. So now what I'm going to do is I'm going to do one more step closer to what LoRa is. So the weight matrices, I'm setting them to different data types here. So this is the part I want to highlight. So by default, LoRa adapters are float 32. And let's say we used a base model that was B float 16. So let's say we're using small LM2 135 million, for example. And so if we look at the data types, we're now dealing with mixed precision. So what we're going to have to do in our forward pass, our kind of sequential forward pass, is we go through our base layer with B float 16, then we switch to float 32, and then we go through our LoRa adapters, kind of quote unquote LoRa adapters. And this is more or less how the PEFT library handles the forward pass, because you have this issue where you have mixed precision between the base layer of your base model and the LoRa adapters that are usually, or that are defaulted to float 32. So our end result, interestingly enough, is B float 16. So not sure how that gets sorted out in terms of PyTorch, but when it adds BF16 to float 32, yada yada, we end up with B float 16. And here's the output. So if I look at the matrix multiplication between my quote-unquote LoRa adapters, it's float 32. The base layer, or quote-unquote base layer, B float 16. The quote-unquote merged base layer is float 32. So I'm going to set my merged linear layer, which is going to be float 32. And then I'm going to pass through my X, and I'm going to get my merged output. And we can't fully see the visual, but here's 2661, here's 2656, here's negative 6953, here's negative 6972. So we're already seeing kind of visible differences in our outputs. And this is a float 32 output. And if I look at all close, when we're looking at the default, which I think like absolute tolerance, I think is like 1E negative 8, and like relative, I think is 1E negative 5 or so. So when it does not meet that threshold, it's above that threshold, so it's not close enough. And when we look at the percentage difference between the two, it's now 2.36%, which is the most so far. So at this point, I think, or initially when I thought that the main difference between merged and unmerged was the forward pass, that may be partially true, but I don't think that's the main story. I think the main story is that you have this mixed precision between LoRa adapters and the base layer, and that mixed precision is, causing a difference as well. So, yeah, I think, both things are at play. Different forward passes for sure, but also mixed precision. So I think both play a factor in having different outputs. So I've summarized the outputs here. So here are my linear output versus the matrix multiplication for 1, 2, and 3 layers. Interestingly, 3 layers is an order of magnitude less than 2 layers, so I don't want to read into too much there. Our matrix addition plus matmul is similar. Uh, then when we do our sequential linear versus merged linear, 3 layers, and we go from float 64 to bfloat 16, we now do see an increase, and it's pretty significant, right? This is by a billion times larger here, and then what would that be? Maybe 1,000 times larger here, and then like 10 times larger here, 5 to 10 times larger here. And then when we do that, but we do it with mixed precision, we get another increase in our relative error. So I want to wrap these things into a function. So I have my mixed precision operation in a function, and I'm using kind of, quote unquote LoRa rank of 16, and then the other size is defaulting to 32, but I want to be able to iterate different sizes. Everything else is pretty much the same. Yeah, so that's our mixed precision. And then I'm going to iterate over these sizes from 32 up to 8,192. And then I'm going to iterate over these precisions, including our mixed. And I want to store this relative error, this percent that we've been looking at, in this results dictionary so I can make a plot of it. Cool. So if we take a quick peek at results, we can see that generally speaking, as the matrix gets larger, float 64 error gets larger, float 32 error gets kind of larger, not significantly. This goes from 009 to 049, 02, 0.4, 0.02 to 0.27. So there is definitely an upward-ish trend. So I'm going to make a plot to look at these results. And here is what we see. And let me zoom out so we can kind of see this. So here's our float 64 at the bottom, which is, at least 8 order of magnitudes smaller when we look at the relative error, which is the percent difference between our sequential linear and merged linear outputs, the mean absolute difference. Then the next best is, or next closest, is float 32, then float 16, and then bfloat 16 and mixed are kind of competing, and the y-axis is a little, I don't know if this is the best idea of axes, but yeah, I will keep it for now. But this goes from like 10 or 10 to the negative 2 to 10 to the 0. So you can't really see the increase. I think the most interesting standout is, so this would be 100. So this would be from 64 to 128. There's a jump for whatever reason. And then everything comes back down again, and then it slowly increases again. But I think it's, the main takeaway I have from this is, twofold, which is what I said earlier when I was looking at the mixed precision, sequential versus merged, is that the different forward passes make a difference, and the precision makes a difference, especially when you have mixed precision in play. So yeah, I'm gonna leave it at that. I guess one more thing I could say is matrix size also seems to play a part, because as the matrix size increases, we get generally higher relative error. And yeah, I think that's all I want to say about this. Again, I think the lessons learned from here are interesting. I think I definitely feel like I understand floating point errors a bit more, or at least I'll be aware of them a bit more. But I don't know if I can extrapolate anything I'm saying here to, transformers or, language models where, such and such precision is going to lead to such and such performance errors. Obviously, it's more complicated than that. There's a lot of research on quantization, and you also get some unexpected performance trade-offs. I was reading this thread this morning in the PEFT repo where someone was saying how they trained LoRa adapters at bfloat 16, not the default float 32, and they saved a ton of time and memory, and the performance didn't really deteriorate. So, you know, precision doesn't always translate as significantly as this chart would lead us to believe. So, yeah, I think I'll leave it at that for this video. Thanks for watching, and I will see you next time.